Here we have data from the orbital simulation. Ratio of orbital radius to Earth radius goes 1.2 up to 2.4 by steps of 0.2. People observed orbital radii of 7,200, 6,675, 6,000, 5,900, 5,575, and so forth. And we see, among other things, that these things change by less and less each time, or at least they tend to change by less and less each time. In green here we have ideal data that we actually obtained in the next class, and we'll see how that works in our next class. But these are the ideal data, and we see that the simulation is very close to the ideal data, except this point, which was, I think, done a little bit carelessly by the individual that did it. This point, which is far out and may be subject to a few little anomalies in the program, because I know this one was done carefully. We can linearize this data by squaring it. If we square all these, then these things will have about equal increments, and these numbers would have equal increments down to their precision. And so we say that the velocity of the orbit is proportional to the reciprocal square root of the orbital radius. Okay? And we note that for a circular orbit, the velocity is always perpendicular to the radial vector. The radial vector is the vector from the center of the planet out to the orbit, so that this and this always make right angles. So if you're setting up the simulation, it doesn't matter at what angle you start your simulation. If you start your velocity vector at a perpendicular, then you have at least a chance of modeling a circular orbit. If you don't, you have no chance at all, because you've already violated the condition of a circular orbit. To get a circular orbit, of course, you have to match the velocities. The velocity has to be just right, or you go out into an eccentric elliptical orbit. If you start anywhere but at a perpendicular to the radial line, you'll go into another elliptical orbit. Turns out that elliptical and circular orbits are the only possibilities.